Okay, welcome to example number 3 in our discussion of binding energy. A nucleus is a bound system. That is, you will need some energy that you have to supply to disperse the nucleons that are holding the nucleus together because of the nuclear bonds between them. So the total mass of the nucleus is always going to be less than the total mass of all the constituent parts that make it up. That's the protons and the neutrons. So the binding energy is really that energy that you need to supply to a nucleus to disassemble it into its individual protons and neutrons that make up this nucleus. So it's the energy that you need to supply to separate this nucleus into all the little parts. So to calculate the binding energy, we find the energy of all the protons, Z number of protons, and N number of neutrons, and then we subtract the total energy from the nucleus from that energy of all the constituent parts. So you end up basically getting E equals mc squared. That delta M here is called the mass defect. And that mass defect is the difference of the mass of all the constituent parts. That's the number of protons here and the number of neutrons. And notice I'm taking the number of protons and multiplying by the mass of protons, and the number of neutrons n multiplied by the mass of the neutron, and subtracting by the mass of the nucleus. And we will get what's called the mass defect. If we take that mass defect and multiply by the speed of light squared, you'll get the binding energy. Now, it should note too that in the typical periodic table, or if you look at the isotopes of different elements, the atomic masses that are listed all along here do not include electrons. Okay, these are masses including, oh actually sorry, I said that wrong. These are including their electrons. So this is the reason why we include them in electrons, is because these are neutral atoms. So let's move on to example number 3 now. And in example 3, we're asked to find the mass defect, the total binding energy, and the binding energy per nucleon of the common isotope carbon-12. So let's write down the given information. Okay, so here's the mass of the carbon-12 atom here, and it's 12.000 atomic mass units. We have a proton, well, we're using the hydrogen atom actually, because the hydrogen atom has a proton and an electron included in this mass, as opposed to just using the proton. I could do it in a longer way and include the mass of electron, but since this is a neutral atom that also includes the electrons, we're going to use the proton, or the hydrogen atom, that includes the electrons as well. So this is essentially, we're going to multiply this by the number of protons, which is 6, and in the number of neutrons, which is 12 minus 6. So we're going to use 6 as well here. So let's move on to finding the mass defect. The mass defect, which would be here, is the mass of all the constituent parts. So that's Z protons times the mass of the proton plus N times the mass of the neutrons, and then minus the mass of the nuclei. So that would be 6 times the mass of the hydrogen atom, 1.007825 U. Remember, I'm using that because I including the electrons in here, and then electrons are also included in the mass of the nucleus, so I don't have to add and subtract here. Then I have neutrons, 6 times 1.008685 atomic mass units minus the mass of the nucleus, which is 12 U's. So go ahead and calculate that, and you should get 0.09894 U. Now I did make a mistake here earlier. I put 8685, but it was supposed to be 8665 here, and so I fixed it up. So again, 0.09894, and that is the mass defect. So now let's move on to calculating the binding energy. The binding energy we'll just write as BE, I guess, for binding energy, is equal to the mass defect multiplied by C squared. The mass defect is 0.09894 U, and we're going to be multiplying this by C squared, but it would be convenient to write this in mega electron volts per C squared. We multiply this by 931.5 mega electron volts per C squared. To cancel out one atomic mass unit here, you'll get your answer in mega electron volts. and you'll get 92.16 mega electron volts per c squared, and you can see that these c squareds here and this c squared here cancels out. So that's the binding energy, and if we want to find the binding energy per nucleon, that's the atomic mass number, you would take 92.16 mega electron volts per c squared and divide by how many nucleons. And the number of nucleons, we have 6 protons and 6 neutrons, that's 12. And that gives you a binding energy per nucleon of 7.68 mega electron volts per c squared. Well, not per c squared, per just mega electron volts per nucleon. And I should fix up a few little things here as well. And there we have it. We have a mass defect of 0.098494 atomic mass units, a 92.16 mega electron volts of total energy, and then 7.68 mega electron volts per nucleon. And that's it for example number 3.